When you take a soluble solid and you put it into water, it immediately starts to dissolve. However, as more and more particles start to form, more and more ions form from the dissolving solid, they start to interact with each other more and more often, and at some point they start to form the solid back and start to form back into that precipitate. At some point, the rate at which you have the solid turning into ions and the rate in which the ions precipitate back into the solid start to equal one another, and so we have equilibrium. And thus we have the formation of solubility equilibrium. Solubility equilibrium looks like this. You have the solid turning into ions, but you also have the ions turning into solid. Thus, the equilibrium. Since it's an equilibrium, it has all those neat things that go along with equilibrium, such as equilibrium constants. The equilibrium constant for solubility is called the solubility product constant. It's abbreviated KSP. There are also going to be equilibrium expressions. The equilibrium expressions for solubility look like this. Notice that the solid is not included. It's never included. Now you can use the KSP to figure out the solubility of a compound. You can also use the solubility to figure out the KSP, which we're going to look at together here in a little bit. One thing that you need to make sure that you know, though, a lot of times when we first get started on this, students will confuse solubility and solubility product constant. They're not the same thing. Solubility is how much can you dissolve into a solution before it becomes saturated. It's measured in grams per liter or grams per mole, and it can change. It can change if you change the concentration of the solute. It can change if you change the pH, which we're going to look at in the next section. The solubility product constant, on the other hand, is the equilibrium between an ionic solid and a saturated solution. It doesn't have any kind of units at all, and it only has one given value for any kind of solute at a very specific temperature. And so if I have a solution of calcium fluoride at 25 degrees Celsius, it has a very specific KSP. I can change its solubility around by changing its pH or changing the concentration of the solutes, but its KSP, its solubility product constant, won't change. Now you can also use the KSP to compare solubilities if you're comparing two salts that form the exact same number of ions. So for example, if I was comparing NaCl and KF, both of them formed 2 ions when you put them into solution, and so their equilibrium expression is going to look something like this. And so since they have the same number of ions that they produce, whichever one has the higher KSP is creating the most cations and the most anions. That means that it's producing the most ions, period. Therefore, it is more soluble. It's forming more particles when you drop it into water. But if you're comparing two salts that have different numbers of ions, you can't just look at their KSP and figure out their solubility. That's because their ratios are different, and therefore their equilibrium expressions are different. So if they have the same number of ions, the higher KSP is the most soluble, but if they have different numbers of ions, you can't use the KSP to figure out which one's more soluble. You have to go through and figure out the values for X or do an ICE table or something like that. So let's look at a couple of examples of equilibrium problems dealing with solubility. First, we're going to calculate the KSP for a compound, then we're going to use the KSP to figure out the solubility. So we're going to do either way. Looking at this first example, we have some silver chromate that's dissolving into water. It tells us it's a saturated solution, and it tells us the concentration of the silver ion in the saturated solution. To do this, the first thing you're going to start with is your equilibrium equation, and these equilibrium equations all look pretty much the same for solubility. You have your solid dissociating into ions. So this equilibrium equation is going to look like this. The thing that most students miss whenever they write equilibrium expressions for saturated solutions is this right here and this, and both of those are really important. Now that we have the equation, we can take this concentration of silver ion, and if we have 1.3 times 10 to the negative fourth molar of the silver ion that's formed, and we know this is formed in a 2-to-1 ratio, that means that we must be forming half of that in chromate ion. So we have our two equilibrium concentrations. We can take these and we can plug them into our equilibrium expression. Our equilibrium expression is going to be this right here. Don't forget this 2 right here. Everyone always seems to forget it, and we don't want to. And again, our solid is not involved in the equilibrium expression. So I can take these numbers that we got here and go ahead and plug them in. And when I do this, I get about 1.1 times 10 to the negative 12th. Now this is a really, really small KSP. So what does that tell us about this? First off, it tells us it's not very soluble, really. And this makes a lot of sense. It's a silver compound, and we know silver compounds tend to not be very soluble. And so this is the type of number we would expect to see for a very slightly soluble compound. Now let's take a look at the second example problem. In this problem, it gives us a value for KSP. It asks us to find the solubility. You start out the same way with your solubility equilibrium equation. So let's start with that. Now once you have this, there's a couple of ways you can think about this. If you want to think about it as an ice table, you can do that. It doesn't matter how much solid you start with because the solid's not a part of the equilibrium expression. But you're starting out with 0 of both of these. You dump in the solid and it's going to change by going up by x and 2x. Alright, because of that 2 right there. Don't forget that 2. Which means that your equilibrium values are going to be x and 2x. Now you have a value for KSP, it's 3.9 times 10 to the negative 11th. You know that that's going to be equal to your concentration of your calcium ion and the concentration of your fluoride ion squared. Don't forget the squared. So I can take these values and plug them into my equilibrium expression. If I take these numbers and plug them in and solve for x, I get an x value of about 2.1 times 10 to the negative fourth. Be sure that you try that on your own calculator and that you can solve for x in this kind of problem. So what does this value for x represent? Well, this is the amount of the calcium ion that was formed. If I multiplied that by 2, it would be the amount of fluoride ion that was formed in my saturated solution of calcium fluoride. That means that this is also equal to the amount of calcium fluoride that was dissolved. And this is a molarity that we just found, and so that means that this is the moles per liter. So what we can do with this is we can take the amount of the CaF2 that dissolved per liter of solution, and we can change moles into grams by using a molar mass. And we can get the solubility of CaF2 in grams per liter. If we go through and solve this, we get about 0.016 grams per liter. Now again, like the last example, this is a pretty small number. It can, in a whole liter of water, it can only dissolve 0.016 grams. But it makes sense that it's really small because our KSP was really small as well.